Hello guys, the purpose of this video is to introduce you the concept of recurrent neural networks and how it is being used to make a chatbot. So first of all, I will try to introduce the architecture and then I will demonstrate the working of the chatbot. So this is the diagram of an encoder decoder RNN. Let me try to tell you why we are using this. In a chatbot, uh, two people are talking, two people are interacting each other. So when one person says something, it is a sequence of words, and to that the other person will respond. That is another sequence of words. So for one input sequence of words, the chatbot has to generate another sequence of words. The first one is called input sequence, and we call the other one as a target sequence. The chatbot has to generate the target sequence. This is the problem that we have. So this is commonly known as sequence learning, and a simple strategy for general sequence learning is to map the input sequence of words to a target sequence. How do we do that? We will first map the input sequence to a fixed size vector. We will use a RNN for this to map input sequence to a fixed size vector, and this is called encoder. And we will use another RNN to decode the fixed size vector representation to a target sequence. So that is how encoder decoder architecture is born. Here in the diagram, on the left hand side, these units are the LSTM cells of the encoder, and these blue units are the LSTM cells for the decoder. So that is the idea behind encoder decoder RNN. Why we are using it for chatbots, or it can also be used for translation. It can be used for speech recognition. Anywhere where there is the input size can't be fixed, we can use this. So I will try to briefly explain this diagram. Let's take an example of you saying, "Are you free tomorrow?" This is the input sequence. It contains 4 words. Are you free tomorrow? So this will go to each word will go to one LSTM unit. R will go to this LSTM unit, and this, as you know, LSTM will have hidden states, which is a representation of the input word, and the second cell, LSTM cell, the hidden state of the second LSTM cell will have, it's a function of the first word and the second word also. Similarly, for the third block, it will be a function not only of this word but also R and U, the first and the second units. So when we carry forward, the output of the encoder LSTM units at the final state will be a neural representation of the whole input sequence, "Are you free tomorrow?" 4 words. So this neural representation is called thought vector, and we use another decoder RNN. It's another stack of it's a recurrent unit of LSTM, and this decoder will take in the thought vector and will try to calculate the probability of each of the words in the vocabulary, and then we will take the maximum probability word and we will output this. So the first unit will output the first word, and in the second unit it will take in input as it will take the vocabulary as well as the previous state as input to generate the second word. So this is how the output is generated. So for the input, "Are you free tomorrow?" you will get output as "Yes, what's up?" 3 words. It can be different also. So we will see the encoder decoder network in more detail in the next slide. So this is the architecture diagram in detail. Here the blue ones represents the encoding units, and the red ones represent the decoding unit. This is a projection layer, and this is the output. So here the input sequence is different. The input sequence is how are you there. So the bottom layer is the embedding layer. That means we will convert the words into vector, because machines can process only numbers. We will use embedding to convert word to vector, word to number. So there are multiple types of embedding available: word to work, globe embedding. So many are there. We are using one type of representation to filter out the most commonly used words. We will filter out the rare words, and we will use only the most commonly used words. And we will pad the vector, and it will be input to the it will be given as input to the encoder units. That is the dark blue cells. There is multiple layers of RNN is there, LSTM is there. So here, how are you there is being trained by these encoder. He is being encoded by the encoder units. It is fed to the decoder units, and this decoder unit will output a vector in the projection layer, and this vector contains the probability of all words in the vocabulary, and here we will take the maximum, we will take the argmax of all the probabilities, and it will output I. So here on the right hand side you can see the equation. It's a conditional probability equation. That is what essentially we are doing here. So each unit in the decoding unit will try to find out the next word in the sequence based on the vocabulary and the output of the previous states, all the previous states. Here y1 to yt minus 1 represents the output of all the previous states in the decoder, and this is the vocabulary vector v. So given all these, what is the next output? What is the next word having the maximum probability? So here after I, the maximum probability will be am. So this represents the conditional probability to generate the output sequence. So this pi represents the product. So basically this network will maximize the product of the probability of all the words in the sequence. So the output sequence will be having the maximum probability. So here this is an example. So the input sequence, as we know, it is how are you there. So this is the p y1 given vocabulary v is the output of the first decoder unit. So let's assume we get a vector like this. This is the vector in the projection layer. So this is a probability of the word banana. Banana is one word in the vocabulary. No, rigid, I, since, and fine. So let the probability be these values. So we will take the argmax of the probabilities. That means the argmax of the probability of all the words in the vocabulary. And here in this case, it is the maximum probability is for I, because for how are you, it usually starts, the response usually should start with I. So this will be selected as the first word of the output sequence. In the next iteration, the next unit, this I along with vector v will be given as input, and we will do the same processing to produce another set of probability for all the words in the vocabulary, and we will do a argmax of this. Then that will be carried forward to the next unit, and we will do the same. There's a slight difference in the training phase and the inference phase. In the training phase, we already know the words. The next word we already know, I am fine. So we will not do the carry forward. Only in the inference phase, we will do the carry forward. Feed forward, we have to set as true. So this is how it works. So let's try the chatbot. How is it working? So now I'm going to run the chatbot interface code. The network is already trained, so I will just run the interface, and this is a simple interface to interact with the chatbot, and this will code the decoder LSTM to do the prediction. So let me try to chat with the chatbot. So it is trained with my personal data as well as some other data as mentioned in the dataset. So I will just say hello to the bot. Okay, the bot is saying, hi, how are you? It's a friendly bot. I will say, okay, good morning. Okay, bot is telling us back, good morning. I'll just start off with some casual chat. How are you? Okay, bot is saying, I'm good. It's verbally correct. I'll just ask the same question in a different way. Let's see. Okay, the answers are consistent. So let me ask the bot whether he's a bot. Okay, it's bot is saying I'm a human emotion of a robot. Okay, it's claiming to have emotions also. Here we can see the output and I mean the input and the output on the right. I will ask, who are you? Okay, the reply is interesting. Bot is saying I am a bit of you. That means it's me. Okay, that's interesting. So I will try to use some chat language, chat lingo that I daily use. When is your birthday? Okay, so the reply is don't know. This is to be noticed because I mean this is the way I always say don't know. So that means the bot is able to learn my talking style. It is something to be noticed, yeah. So what else to ask? What are your hobbies? It's saying I like gaming and painting. Okay, I think it is coming from the secondary database, not my personal chat, because these kind of questions are not always asked between like personal chat. It's coming from the other dataset, but the reply is consistent. What do you do for living? Just okay, the bot is saying I'm a retired gym teacher. I am okay, it is repeating I am twice. It's a grammatical mistake, but that is expected of generative chatbots. Grammatical errors or offensive things are like it can come in generative chatbots. Otherwise we need a huge dataset and so much of training to get rid of this problem, but that is fine. I mean the response is almost consistent. So I will ask something else. Okay, something unrelated now. I will just say that's better. Okay, the bot was not able to understand. What? Tell me. But here you need to notice something, that the language it is using is my language. I always use this spelling for what and this for tell me. So it is talking like me. It has learned my way of saying. Now I will try to ask the feelings of the bot. So it is saying I'm doing great. How about you? Okay, so the bot is doing great. So some more emotional questions. Okay, it is saying me too. This again is my way of saying two. I always use the digit 2 instead of word. So it has learned my way of talking. That is the notable thing. let me divert the talk. Do you drink? Okay, it is saying yes, I like water, I love them. Chat is being funny. I was not asking about water, obviously. Okay, so now something else. Okay, I will try to say something in my native language. I will try to scold the bot. It is scolding me back in our native language. Consistent reply. Okay, let me ask whether she is hurt. Okay, she's saying it's she's not sure, or maybe sad. Okay, not hurt as well as sad. Okay, good. So something else, some other question. Do you like to read? Okay, I do. I like to read. Okay, that's good. Okay, now do you like movies? Okay. Chat is becoming naughty. So let's say goodbye to the bot. Let's say bye. Okay, bye. Chat you later. It seems. I mean, chat bot seems to be in an urgency to end the chat. Let me see. Okay, the bot is sleepy. That is why. Okay. Okay. Oh, great. See, this exactly is the way we talk in chat. I mean, the spelling, the tone, the context, everything is right. So chat is the bot is performing very nice, but I have to admit that there are many questions which the bot cannot give a good answer to. We have seen some grammatical errors and some offensive ones also, but that is part of the game. I have used only a very small data set of my personal chat and a lot of other conversations also, because that much only was available. If you have more personal data, then the bot will perform even better. But first of all, you need to convert your personal data file to YML format. You can use the parser given in this project in the GitHub. I mean, if it's a HTML file or a JSON file, then you can use it. Otherwise, if it is of some other format, you may have to write your own parser and your own conversion to YML. And you may have to even tune some hyperparameter also, like the learning rate, batch size, step, and all. Here I am using 7 into 10 raised to minus 3 as learning rate, and steps around 25,000 steps. You may have to increase if a data set is more. Try it out. I mean, you have to find the right balance. So you can definitely make the chatbot better performing. Happy talking to the bot. Thank you.